Right, guys, in the last lecture we had looked at the bisection method, and the conclusion that we had come to was that bisection method converges. Unfortunately though, bisection method is relatively slow. It's linear convergence, and I promised you that I'd look at a couple of methods that had faster convergence, quadratic convergence for example, for solving nonlinear equations. But before I do that, what I want to do in this class is to talk at some length about Taylor series, and we're going to use Taylor series all over this class repeatedly. So I want to make sure that you're very, very comfortable with the Taylor series. And so in this lecture, I'm simply going to talk about what Taylor series is, what is the residual or the error when we truncate a Taylor series, and how we characterize this error. All right. So the Taylor series, as you might have seen in your high school classes, follows the Taylor's theorem. Okay, so you're given a function f. The theorem is as follows. Let the function f prime, f double prime these are the n+1 derivatives of the function. Let's say they are all be continuous in the interval a, b. Okay. We'll also assume, actually we're only going to assume that the first n of them are continuous. And I'm going to assume that and the n plus first derivative exists in this interval. Okay. So once again, f, the first derivative of x, the second derivative of x, all the way through the nth derivative of x are all continuous in the interval a, b, and that f n+1, the n plus first derivative, exists in the interval. Okay, then there exists number eta such that f of b equals f of a plus b minus a times the first derivative of x, the function computed at a, plus b minus a whole square divided by 2 factorial, the second derivative computed at a. Okay, and this goes all the way through to b minus a to the power n over n factorial f, the nth derivative computed at a. Okay, and then there's an error term after this. You may or may not have seen this error term before in your classes. This is simply b minus a to the power of n plus 1 divided by n plus 1 factorial, and this is f, the n plus first derivative computed at some point eta, okay, where this point eta belongs to the interval a and b. Okay, so you've probably seen the infinite Taylor series. This is a finite Taylor series with the residual term. So this simply says that the function at value b is fa plus b minus a times the first derivative at of f at point a, b minus a whole square divided by 2 factorial, the second derivative computed at point a, all the way through to the nth derivative computed at point a multiplied by b minus a to the power n divided by n factorial. But if you were to stop this in a finite approximation, then you have a residual error term, which is b minus a to the power n plus 1 divided by n plus 1 factorial times the n plus first derivative of f computed at some point in this interval. Okay, so I haven't told you what this point is, but that it exists within this interval. Okay, so remember this. This is an extremely important expansion. The error term is extremely important as well, because we will use the error term over and over to compute the error in this finite approximation, if we do a finite approximation. Okay, there are other forms of this Taylor series as well that are important. So let me write all of those down as well. So let me erase this. So if the expansion is around a given point A, okay, then you can write the Taylor series. This is nothing deep. I'm just rewriting the previous expression in different forms. You can write this as f of x. Remember, I'm going to expand this around point A. So I'm going to write this as f of A, okay, plus x minus A times f prime at A, okay, plus x minus A whole square, the second derivative computed at A divided by 2 factorial, plus all the way through to x minus A to the power n divided by n factorial f the nth derivative at A. And then there's a residual term again. So the residual term once again is plus x minus A to the power of n plus 1 divided by n plus 1 factorial times f n plus 1 at some point eta again. Okay, so the point eta is in the interval x between x and a, or a and x, okay, depending on which side of a you are. Okay, so once again, it's exactly the same expression. In fact, if you simply replaced b by x, you would get exactly this expression from the previous expression as well. But this is called the expansion around a fixed point A. Okay, so remember this, and typically what we will do is we will take a finite approximation to this, which will only include up until here. So that's an approximation to the function, and that is the residual error. So this is also sometimes called Taylor's theorem with a remainder. Okay, so let me formally go ahead and write the remainder. So the remainder in computing the function fx, so I'm writing this as remainder with an nth degree Taylor series approximation for the function fx. This is simply fx minus the finite approximation that I've taken here. Okay, so I'm simply going to write this as sigma of j equals 0 to n. This is x minus a to the power of j divided by j factorial times fj at point A divided by, I'm sorry, j factorial is all over here. Okay, so remember, this summation is the finite approximation that I've talked about here. Okay, so that's simply x minus a to the power of j divided by j factorial fja. Okay, so this is the finite approximation, this is the real function. So what should remain is just this term. Okay, so from here you can simply write this as this is x minus a to the power n plus 1 divided by n plus 1 factorial f n plus 1 computed at some point eta in the interval between x and a. Okay, now this term, which is the error term, this is the error term in the finite approximation. This error term can also be written as big O of x minus a to the power n plus 1. Okay, so what this tells you is that if you have a finite Taylor series approximation of degree n, then you have an error that roughly goes as degree n plus 1. Okay, so there are a few things that you must know about Taylor series. Let me go ahead and write them down. So the first important thing you must know is, depending on properties of f, Taylor series may converge everywhere. Everywhere, okay? It may converge in specific intervals. Okay? Or it may only converge at the point itself. Okay? So don't assume that the Taylor series will converge everywhere. Okay? So the second thing you need to know is you will encounter nice functions. I'll call functions such as e to the power x, sine x, cosine x, converge everywhere. Okay? And finally, you might have heard of the term Maclaurin series. So a Taylor series around point 0 is also called the Maclaurin series. Okay? So once again, Taylor series is extremely important. You need to know this very well. Not just for expansions, but also for characterizing convergence rates, errors, and we will use all of this even in our next lecture, and then we will use it all through this class. Okay, let's take a few examples of this. So the first example that I want to do is, let's keep it simple. Example. What is the Taylor series of a Taylor's expansion of e to the power x around x equals 1? Okay, so this is the question that's given to you. You'll notice that this is actually kind of easy. The reason this is easy is the derivatives of e to the power x are all e to the power x. Okay, so you know that f of 1 is simply e to the power of 1. Okay, now you know that the derivative of e to the power x is e to the power x itself. So you know that the first derivative at x equals 1 is simply e to the power 1. The second derivative at point 1 is e to the power 1, and so on. All derivatives are just e to the power of 1. Okay? So using my formula that I gave you earlier in this lecture, I can simply write e to the power of x as the function evaluated at point 1. This is f1 plus, now this is x minus 1 times f, the first derivative at 1, divided by, of course, 1 factorial, so I'm not going to write anything there. Okay, plus x minus 1 whole square times f, the second derivative at 1 divided by 2 factorial, plus, let me just write one more term, x minus 1 cubed divided by 3 factorial times f, the third derivative at 1, and so on. Okay, so this is simply the Taylor's expansion. Now, you know that all of these are simply e to the power of 1. Okay, so I can write this as e to the power of 1 times, that's just 1 plus x minus 1 plus x minus 1 squared divided by 2 factorial plus x minus 1 cubed divided by 3 factorial plus. And that is your answer. If you wanted to write this in a summation form, this would simply be e to the power of 1 summation from j equals 0 to infinity. This is x minus 1 to the power of j divided by j factorial. Oh, I'm sorry. Yeah, we're good. J factorial. Okay. So this is a simple example. Make sure you can do this. This is extremely important. Let's look at one more example. Just make sure I didn't make a mistake here. No, I think we're good. All right. So the next example I'm going to do is what is the Maclaurin series I'm going to do this for the function cosine x. Okay, so let's once again compute the function. Remember, the Maclaurin series is the expansion around 0, so I'm going to have to compute f0, the derivative at 0, the second derivative at 0, and so on. So what is f0? f0 is simply cosine 0, which is 1. Okay, now the derivative f prime 0, the derivative of cosine x is minus sine x. Okay, so this is minus sine 0, which is 0. Okay, now the second derivative is the derivative of this. The derivative of sine x is cosine x, so this is minus cosine 0, which is minus 1. Okay, the third derivative is, and of course the derivative of cosine x is minus sine x, and that's a minus. This becomes simply sine x, so this is sine 0, which is 0. Let me do one more. The fourth derivative at 0 is the derivative of sine x, which is cosine x, and this is simply cosine 0, which is 1, and so on. Okay, so from here I can almost immediately write cosine x equals, of course this is f0 plus x times f prime 0 plus x squared over 2 factorial times f double prime 0 plus x cubed over 3 factorial times f, the third derivative at 0, plus x, let me write one more since I computed that, x to the power 4 over 4 factorial times f 0 plus. Okay, so this simply becomes, what is f0? f0 is 1. Okay, now what is the first derivative? This is 0, so this term vanishes. So this is x squared divided by 2 factorial times the second derivative. The second derivative is minus 1. So I'm going to write this as minus x squared over 2 factorial. Okay, remember this term became 0. This is minus 1, so this becomes x squared minus x squared over 2 factorial. Now the third derivative once again is 0, so this term becomes 0. The fourth derivative is 1, so this becomes plus x to the power 4 over 4 factorial. Okay, and so on. Okay, so you can write this in some summation form as simply summation k equals 0 to infinity minus 1 to the power of k x to the power of 2k divided by 2k factorial. Okay, so that's a simple Maclaurin series expansion of cosine x. So remember, the takeaway from this lecture is two things. One, you must know the series expansions. Understand that the series may not converge everywhere, it depends on the nature of the function f. And just as importantly, you need to know that there's an error term which is typically x minus a to the power of n plus 1, where a is the point around which you're doing the expansion. Okay, so there's n plus first power of error when you take a finite or an n degree approximation using a Taylor series. All right, so we will use these results in the next class when we introduce Newton's method. Thank you.